Hello, folks. Welcome to lecture 5.2. We are in the chapter Chemical Quantities, which was covering the mole, and Introduction to Chemical Reactions. And now we're going to combine those two topics to talk about chemical equations. So as a reminder, right, we've kind of worked through this progression from elements and atoms into compounds and different types of compounds and how compounds interact with each other through intermolecular forces. And now we're going to be getting to changing molecules. So chemical reactions involve one thing turning into another thing. And how do we know that a chemical reaction has happened? Chemical changes can be observed in possibly these following ways. So if you see a change in color, right? So if you go back to this slide, see all these different beakers and flasks in the background, right? They all have different colors of solutions. So if you mix two things and the color changes, then that's evidence of a chemical change. If a solid forms, that's evidence of a chemical change. If heat is produced or absorbed, so if something gets hotter or colder, like an ice pack that you crack open and it gets cold, that's evidence of a chemical change. If a gas is produced, that's evidence of a chemical change. And if a smell is produced, then that would also be. All of these are just in general bonds breaking, new bonds forming, right? In the most general definition of a chemical reaction, we would say it's breaking present bonds and forming new bonds. So changing the way that atoms are arranged and bonded to each other. We're going to want to think about what's happening at the level of the molecule, so at the molecular level, and that's how we're going to try to make sense and have a model of what's happening with chemical reactions. So recall that atoms, ions, molecules, particles, anything at this level is in constant motion. Okay, even if it's in a solid phase, it's going to be vibrating around. If it's in a gas phase, it's literally just flying through the space, right? So they're always in constant motion, which means these molecules will collide with each other. Okay, think of it like billiard balls on a pool table, right? And if they're all randomly moving around, eventually they'll hit into each other and bounce off, right? And most of those collisions will just essentially be a bounce off. They'll just bounce away from each other. However, if those collisions have enough energy, it'll actually cause a chemical reaction to occur. So in the next section, we'll talk more about energy and things like the activation energy. But for now, we can just think about it in terms of these simple terms, right? That we have some, we'll call them molecules, but that means atoms, ions, particles. We'll just call them molecules, um, moving constantly through space, such as maybe an O2 molecule and an N2 molecule. So at some point, let's say these two will collide, as evidenced here by uh, the big starburst, right, which indicates, oh, there's energy involved here. We all know that from comic books and shows and stuff. So it's like boom, like collision, energetic collision, and what comes out on the other side is two NO molecules. Okay, and so you can see that what happened was we had an O2 and an N2, and you might recall the Lewis structures here, just to be accurate. If I can get my dots to draw. There we go. Oh boy. So what happens when they collide? That this bond is going to break, this bond is going to break, and we'll see they'll basically swap, right? An N and an O will go together, and an N and an O will go together. And then what we get is two NO molecules. So that's just an example, right? But in any kind of reaction, you have to think the molecules that are reacting have to come into the same space together. They have to interact. They have to come into contact in order to actually initiate this chemical reaction. So one way that happens is a collision with energy and the correct orientation as well. Okay, so we have what down here is a balanced chemical reaction, right? We can't say that we take an N2 molecule and an O2 molecule and we make NO, because that's like, well, what happened to the other N and the other O, right? And this gets to the law of conservation of mass. It simply states that matter can be neither created nor destroyed. So what this means in our context is whatever you start with, like all of the atoms involved have to still be there at the end. They can be rearranged, new bonds, right? But you can't, things don't disappear or come from nowhere, right? So in this example, another reaction is methane, right? Which you know now is CH4. If that reacts with oxygen, O2, that's called combustion, it will produce carbon dioxide and water. Okay, and notice that there are these numbers here, like the 2. So this is actually already balanced. We'll talk more about balancing, but I'm going to tell you this is balanced. And you can tell if we look over here, right, that the number of carbon atoms that we start with is 1 right here. And in the products, there's still 1. The number of oxygen atoms is 4 on the start, and it's 4 at the end, right? They're bonded to different things, and they look different, but it's still 4. And then there's 4 hydrogens on this methane, and there's 4 hydrogens on the 2 waters, right? And so all mass, all atoms have to be accounted for on both sides. In one type of molecule or another, it cannot disappear. And we can say that the reactants and products are composed of the same number and types of atoms, only the bonds have changed. So back to this N2 and O2, and the example was actually given as the chemical equation, right? And so here we can see what we represented as kind of this figure. In one way, we can also represent by a chemical equation. So the chemical equation describes the chemical reaction. So it conveys the identity of the reactants on the left and the products on the right and their relative proportions. That would be like the 2 here, right? This is called a balanced chemical equation. The balanced chemical equation must have the same number of atoms for each element on each side of the arrow, right? The arrow is kind of like an equals sign, okay? Before the reaction and after the reaction. And so here's another case. So you can count up how many hydrogens, how many carbons, how many oxygens, and it has to be the same on both sides. If it's not, we can add these coefficients. Okay, so more about chemical equations. I've given you lots of examples. Here's that methane one again. So a summary of the parts. A chemical equation always identifies the reactants to the left of the arrow and the products to the right of the arrow. Sometimes, but not always, it will have the physical states, so like solid, liquid, or gas, or aqueous, AQ. And aqueous means it's dissolved in water. So a lot of chemistry happens in a water solution. So aqueous is a fairly common physical state. It will also include the symbols and the formulas of the reactants and products separated by plus signs, right? So it looks kind of like a math equation, where on the left we have our reactants, we have methane, gas, and oxygen gas. The reactants and the products are separated by the arrow, Okay, the arrow is like the equal sign. And we put whole number coefficients to indicate relative proportions. So the 2 in front of the oxygen and the 2 in front of the hydrogen are whole number coefficients to indicate the relative proportions. The balanced chemical equation follows the rules of a mathematical equation, right? So if you add up all the parts on both sides, they have to be equal. Let's talk a little bit more about those coefficients. So N2 plus O2 again leads to the product of two nitrogen monoxide molecules. Okay. You can think of this in two ways. We've just spent a lecture talking about moles and the difference between moles and molecules. Um, the difference is simply just the scaling by the counting unit of a mole. So this ratio represented by these coefficients, right? There's essentially 1 and 1 here that are left off. But it could be individual units, right? It's like one nitrogen molecule reacts with one oxygen molecule to produce two nitrogen monoxide molecules. But we can also talk about molar ratios, which is simply just scaling everything up, right? So 1 mole of nitrogen reacts with 1 mole of oxygen to produce 2 moles of nitrogen monoxide. So that same information shows up in one chemical equation. It's just, are you talking about molecules or are you talking about moles of molecules, right? Okay, one more slide. We'll in part one. This is just another example of coefficients versus subscripts and law of conservation of mass. So this is the combustion of glucose. So we have C6H12O6 plus 6O2 plus arrow, so turns into or reacts into 6 carbon dioxide and 6 waters, H2O. So let's just focus on oxygen here, right? And we can see how many oxygens are on either side. This glucose molecule has 6 oxygens in it. So we can just write 6 for that. The oxygen has 2 oxygen atoms, but we have 6 of the oxygen molecules. So we have 6 times 2, we have 12, for a total of 18 oxygen atoms on the reactant side. And over on the product side, we have CO2 with 2 oxygens, but we have 6 of those, which gives us 12. And each water has 1, and we have 6 waters, so that gives us 6, so that gives us 18, and it is equal. So we can change coefficients, right? Coefficients are used to balance the reaction. We cannot change subscripts, right? The subscripts are actually in the molecular formula, right? And if you change that, you change the molecule, right? So instead of H2O, if you try to put a 2 here and make it H2O2, well, that's hydrogen peroxide. That's not water anymore, right? So we can't change the subscripts because that changes the actual molecule. But what we do to balance is add coefficients. So when we talk about balancing an equation, what we mean is finding the correct set of coefficients that follows the law of conservation of mass. Okay, and we'll pause this here, and we'll start with a question to do exactly that next time.